Then, whenever you're ready, please share your screen.
Can you see everything or?
Yeah, we can see it.
Okay, great. Okay, so I cannot for the life of me think of any sort of bad food pun. And so I'm just going to get started. Uh, so I'm going to talk about the Camembert intercomparison. This is focuses on GCMs, so three-dimensional circulation models, specifically for Mini-Neptunes. You'll hear about the complementary MOCA project, which covers sort of hot and ultra-hot Jupiters right after this. So this is the fourth buffet, and we are sort of a fairly evolved MIP compared to some of the others. My slides are not advancing.
No, they're not advancing. Oh,
Yes.
now they are.
There we are. Okay, sorry about that. This is obviously, so we have a quite a large group now, covering 7 or 8 different GCMs. Our latest addition is Nikolai Euro, who again you'll hear about next or hear from next, and he runs the Puma GCM. But we have ExoFMS, Expert, the Russian Manu GCM, and the Unified Model, amongst others. And they're all sort of trying to do the same project and all sort of go over what our protocol is. The sort of TLDR of everything, just to get it out of the way, is that our protocol has been published. It was published 2 years ago now, and our production runs are underway. And yes, this is essentially what I said last year and perhaps the year before that. The overview, I'll talk about the protocol design, how we chose our targets, and how those targets are increasingly become interesting scientifically. So I guess that perhaps means they were chosen well. Some may say we chose poorly. And then lessons learned and early results. So I guess at this point, a lot of the MIPS have very similar thematic design choices. We wanted to maximize participation. And as far as GCMs go, that meant because of our computational limits on on resources and how long it takes to run a GCM, we had sort of had to limit the number of targets that we looked at. We're not like Malbec where we can do dozens upon dozens of cases. We're really going to just limit ourselves to 2 targets and then perhaps three different cases each. And even then, most GCMs will not take part in all of them. We also had to remove clouds from the protocol because most of the GCMs at the time we wrote the protocol, they did not have any sort of radiatively coupled cloud mechanism. And so they just wouldn't be able to participate in any sort of cloud intercomparison. And so having one, maybe 2 participants doesn't really make a case for the intercomparison at all. That will become an issue because, as we know from exoplanets, they're pretty cloudy. So comparing to actual observations is going to be a bit more difficult in some cases. We also chose to go for fixed simulation times. Now, we do know from some studies that the actual convergence times could be quite long, on the orders of hundreds of thousands of days. And that's just computationally prohibitive and would probably knock out a lot of our participants from actually taking part, if you had to run your simulation for the better part of a year. So we chose targets of 4,000 or 10,000 days, depending on the case. And hopefully we created a setup that didn't require a lot of additional coding. Like you're not adding in new physics into your model. You're not having to modify how things are read in. Everything is fairly straightforward and sort of self-contained. You can run your test case, and if need be, you can rerun your test case with slight modifications. Now, we did choose our targets based on, observations, even though it's unlikely that we will actually reproduce anything observational. Um, the hope is, however, that either through future versions of the protocol that can um, cover clouds, or that can be modified so that they better suit what we know about the targets now, that there will something observational will come out of this. The other option is that people, once they understand their GCMs better, can then move forward and be more confident in their modeling of these targets or similar mini-Neptunes or sub-Neptunes, depending on your choice of nomenclature. Now, one thing that will come up is that, and I think it was mentioned yesterday by Linda, we didn't want everybody to do the protocol before it was published. And part of that was it's just a lot of work. But also, if everybody does the protocol before it's published, then is it really just a protocol? Instead, we had two volunteers. We used the UM and then ExoFMS, and in one case Thor, to actually test different parts of the protocol to see if they were doable and then modified them. This will sort of impact our results, perhaps unfortunately, in the future. And I'll go about that later. Okay, so what are our targets? GJ1214b, which everybody's heard of, and K218b. The former, at the time of writing the protocol, was probably the most modeled sub-Neptune in the literature. So hopefully people were fairly confident in their ability to do that. And the other one is K218b. At the time, there were two different models of K218b, and there was a lot of enthusiasm because of the debate about whether it was methane dominated or water dominated from 2019. And there was a lot of proposed JWST observations. And so it was a fairly easy choice to make to sort of narrow it down to these two. So here was sort of this slide actually is from a few years ago, and it was sort of the argument made for modeling GJ1214b, prior published models. There were some observations already, planned future observations, etc. And well, now we actually have both, we have all those data from JWST in the early cycles, and there's a phase curve. There's, observations with NIRSPEC and MIRI. And what we're finding is something that's very confusing. And so, which reinforces my earlier claim that we're probably not going to reproduce this through the protocol, but I think it makes it a very exciting target to test our GCMs on so that we can sort of move forward and keep trying to understand what on earth is going on with this. And then the other case, similarly, had a few prior published models, had some observations. There was the possibility of water clouds on K218b, just because of the temperature range. Again, we have a lot of published results now from JWST, and then we have even more science questions. Is there a possibility of an ocean? And now you don't observe the ocean directly, but there is aspects of transport. Like, how do you transport things from the ocean upwards? Can we make any sort of understanding of that from a GCM? And then there's obviously, is there an ocean? Is it supercritical water instead? Is this a miscible atmosphere? Björn Benecke, has been talking about the vodka atmospheres. Is the CO2 detection robust? What is the actual composition? There haven't been any new GCM runs, but there's a boatload of 1D models that are coming from all this analyses. And I think that this positions us well not to make claims about the observations, but to be a launching pad for more studies on what's going on with this perhaps controversial, because of the DMS claim, controversial planet. And then here I just have another disclaimer. We're not going to be matching observations, because metallicity is probably different. We don't have clouds or hazes, and definitely understanding the hazes on GJ1214b has been a real struggle, with some papers needing artificially reflective hazes to even get something close. K218b has been just a debate in the one-dimensional models about what the actual composition is, what the deep atmosphere looks like. Here again, transport might be interesting, but don't expect us to be fitting any observations anytime soon. So what does the protocol actually look like? So we have sort of 3 phases for each target. We start out with a classic Held-Suarez temperature-forced test. And that's really because everybody uses their own radiative transfer as well. So having a test that is just temperature forced, with a very simple relaxation, allows us to sort of remove that aspect of uncertainty and then move forward with a test of really the dynamical core. After that, we have a gray radiative transfer. We thought it was important, for multiple reasons, to include gray radiative transfer. First of all, some exoplanet GCMs only support gray radiative transfer, and so we wanted to maximize participation. But also in the literature, there's a number of studies that focused on gray RT, but found very different results. And so that's a place where we can step in and try to sort of understand why they might be seeing, 3 jets versus 2 mid-latitude jets versus 1 very large single, jet at the equator. So I think there is a good motivation for this. And then, of course, the final one is just doing, fixed chemistry, but multi-band radiative transfer. This obviously, again, there are discrepant results in the literature, but this also sort of represents what we will, the most physical of our tests. Now we're taking a PT profile, an initial PT profile, and the chemical abundances from a study done by Ben Drummond for GJ1214b and by Benjamin Charnay for K218b. And so our abundances won't match what retrievals are showing, but that's perhaps something we could sort of modify down the road. And so here's sort of what our temperature profiles look like for the Held-Suarez test. Pretty simple to implement, and most GCMs have done this already. It's extremely weak forcing in the case of K218b, whereas our parameters for GJ1214b are relatively strong, with a few hundred Kelvin difference between the day side and the night side. GJ1214b was fairly straightforward for most of the GCMs, but not all of them to run. K218b has been a real struggle for a few. And this comes back to the issues we had in how we designed the protocol, where we only had a subset of the GCMs to actually test the protocol. So everybody who tested this case were able to do it. However, it turns out that some of the ones who didn't test it are actually having troubles, and now we have to sort of figure out why they might be crashing or unstable. Now, this is obviously sort of interesting from a numeric standpoint, but it does mean that we are sort of inadvertently having a smaller comparison set. Like I said, case 2 is dual gray, and here you can see Kristen Manu's 2012 paper, and then the Wang et al. Paper from 2020, where they have sort of very different zonal jets. This is fairly straightforward to set up. And to be honest, here we have not had a lot of people running it yet, but we have not seen, at least for GJ1214b, any sort of issues. with the dual gray, with one exception. Here, because of how things are set up, we do have some deep atmosphere issues, and some GCMs have required sort of bottom drag to actually maintain stability because of the way the profile is. Now we still have not reached the point with where we have a number of GCMs where we can actually say, oh, we're seeing very different results. And so we can't really speak to why the literature has these yet. And then, again, here is the non-gray radiative transfer. We have all of the usual suspects for our opacity sources. Because we have Malbec people here, everybody here is in Camembert is using their own line lists and their own approaches to radiative transfer. So there's probably, implicitly some differences just in there that will result in differences in the GCM results. But we thought it was best to actually approach it where people just do their own thing, do what they would normally do, sort of like what Amber was saying earlier, to get a better comparison of how sort of a real world differences might happen. Of course, these are of course model worlds, though. Poor choice of words on my part. Okay. We have not had any sort of stability issues here, but again, we've only had a few people run this case. And so, we are hopeful that once everybody has their runs submitted and, we can look at them, everything will be good. Okay. I did make a slide of just lessons. I did mention already that we had some issues with, people who were not involved in the designing of the protocol. Now their GCMs have issues. Interestingly, we have found that how we expressed the protocol was reflected in, or rather, who tested the protocol have their own parameters reflected in the protocol and how it's expressed. For example, how you express the total irradiation, or even what requirements for outputs. Often, what outputs we require in the protocol come from the UM and from ExoFMS because they were the ones who tested it. Whereas other GCMs might not even have those as default options for their outputs. And so providing those data either require them to just to skip it or to, do some coding, which is kind of annoying. And so there is sort of an argument for being more inclusive in the design, at least. The one big takeaway is that the hardest test by far has been the Held Suarez, which is a bit surprising because you sort of think of it as a standardized test for GCMs. It's unclear whether it's just the temperature forcing is the problem or it's the specific input profiles that we're using. Now, how about progress? Because this is a status update. This is our second or third year doing this. We've sort of received a random sampling of runs from everybody. Green means the run is supposedly finished based on what the groups tell me, but we still haven't received the data in a lot of cases, or there have been formatting issues in the data. That's another thing that we've sort of found, that we standardized an output format, and having to sit down and dot all the I's, cross the T's in converting your usual data into this specific Camembert format has been sort of a pain in the ass, to be honest, for some people. And it is unfortunate, and that perhaps is causing a bottleneck of you have to find the time to sit down and actually figure out how to actually convert everything. But other than that, I'm actually quite hopeful. We're just waiting for people to get data converted and uploaded. But as you can see, there's a fair amount of green on this, which means the runs are done, and that's the most time intensive of the parts. And then I'll just show you like two slides. Here's sort of the two of the Held Suarez tests from Expert, which is from the Gratz group, and then Thor, which is sort of Burn. And you can see that there are, differences about 100 Kelvin in the temperatures. The bigger difference, though, is that the equatorial jet is significantly faster in expert. 4 has, we know from the literature, generally slower jet speeds, and we haven't sort of nailed down why that is yet. And then similarly, here's the GJ1214b, the full radiative case. Again, the temperatures actually in the upper atmosphere agree a lot better. Um, uh, uh, and the wind speeds are again a bit faster with expert. We haven't really delved into all the data because we're sort of waiting for to get a more of a quorum of submissions. And so, future plans. Apparently, last year I said initial results in 2024. So that's going well. If you have any other ideas for papers or you want to take advantage of these data once they're, been collected, we're happy to participate. Sort of other projects, ancillary protocols. Obviously, something like clouds would be interesting. But also, how can we use our data to inform initial conditions or be post-processed by other MIPS like Malbec or Risotto? Like for a retrieval, obviously having a 3D structure might impact things as well. And then obviously the biggest one would be with MoCA, you'll hear from Nicola in a bit. A lot of the GCMs involved in that MIP are in ours as well, and we're just looking at a very different part of the parameter space. So it'll be really exciting to see if we get the same conclusions, who performs better, do the same GCMs, agree across multiple parts of parameter space. And then the last one is, can we actually do like 100,000 or a day, 200,000 day run with at least a subset of this to see if there is a potential change in the behavior over longer timescales. And then all the data will be uploaded and made public, as I think Thomas mentioned. And so here's the contact information. Obviously, there's a Slack recently renamed. So yeah, get in touch if you're interested. Thank you.
Thanks very much, Duncan. Are there any questions? Please raise your hand or type it in the chat. While you're doing it, I can ask a question. So speaking of those convergence tests, sorry if you mentioned that, but for how long did you run these cases that you showed at the end?
So cases 1 and 3 were run for 4,000 days, I believe. Case 2 was run for 10,000. We opted to go longer for case 2, which is the dual gray, because that's a place where in the literature the number of jets and the disagreement in the literature was a bit larger, and there was this argument about some transition happening between different flow regimes around 10,000 days, and we thought we could get away with getting some people to run that long.
Mm-hmm. And did you look at any metrics of sort of model convergence, like the radiation balance or something else?
Yeah, so we have the top of atmosphere radiation. So we can look at that. I haven't done an analysis of like how it's changing with time, but that is output regularly from all the GCMs. Some of them output things like axial angular momentum. Others don't, and in that case, we will just post-process the data and get an estimate from that. And that'll actually be an interesting one because obviously I think none of these are maybe Thor is, but most of them are not designed to conserve axial angular momentum. So they do shed it, and that'll could potentially impact your deep atmosphere.
Yeah. Okay, thank you. Any other questions?
Yeah, we just had to add a comment. Well, thank you very much, Duncan, for the very nice talk. I think it's actually it's kind of great that we didn't start Camembert with having clouds and potentially hazes, right? Because we are already uh, he has so much things to compare, even if we don't include them, that if eventually in a future slice of Camembert, there is a need to do those simulation with cloud and haze, we will already have learned a lot without them. A little bit like we did for Thai, where we did those benchmark cases that were dry without water, and we understood a lot of things about the dynamics and relative transfer before being able to include the clouds on the next step.
Yeah, I think there's just so many modeling choices that would go into modeling clouds um, that I don't think we could realistically just have people come with their own cloud model and then get things that are even similar. We would probably have to sort of force them to adopt a lot of assumptions just to get some sort of comparison. Um, yeah, I think I think it's necessary. You know, we should really compare our cloud models, but it is definitely a second step. And you know, and if it takes us a year or two, if nothing else, we can take the time and figure out a good name for a cloud MIP.
That's fair. Yeah, thank you. Also, another question. So you mentioned a bunch of 1D code that I've tried to fit those data. So do you think that would be useful to have few of them as well participating in the results of Camembert, even if they won't have the same outputs and diagnostics, but maybe few of them would be in common? It could be interesting to see how different is the temperature profile or things like that.
Yeah, definitely. I mean, like I said, so Hamish Innes is it actually takes part in Camembert, so he would be somebody who's um, modeled K218b like in 1D as well. Um, but I think it would be interesting to involve some of those. Um, if I can be perfectly frank, the discussions about K218b are a bit contentious right now. And I think staying above the fray might be good for my own sanity. Um, but yeah, I think some comparison would be warranted.
That makes sense. Thanks.
The main question is whether these GCMs include a profile of DMS or not.
Yeah.
um,
Well, I mean,
uh,
like we you know we don't have um, water vapor, and there's all sorts of effects there, and we don't have hazes, and yeah.
yeah, fine. I was going to ask, since we have a bit of time, I was going to ask just in terms of like organizational structure. So after you mentioned that you published the protocol paper 2 years ago, and so have you had any interest from new groups to join, and how was that experience?
So immediately after the publication, we had a bunch of people join. Um,
Oh, yeah.
and that was really like people who like perhaps like different branches of the same GCM, as it were. We'd reached out to some people who didn't feel they could contribute, but then someone else sees the protocol and is like, "Oh, I want to take that on." Yeah, so I think having the protocol published was sort of good advertising and brought on a bunch of people. And then obviously much later this year, Nicola is going to join with Puma. So
Yeah, that's great. That's great to hear. And another sort of evidence or another reason to publish protocol papers separately and well in advance of the actual production runs and results.
yeah.
So
Yeah, like Linda said, if this was sitting on a web page somewhere, we wouldn't have the buy-in that we do. So
Yeah.
And according to the Buffet survey, there are 9 people that would be interesting to join Camembert. So I will send you the emails there. I have the list ready.
Great. Yeah. Yeah. They're welcome to participate.
Awesome.
Thanks, Thomas. Thanks, Duncan. So after this very full menu of risotto, Thai, and camembert, I don't know about you, but I fancy a cup of mocha.